All right, so the last couple of days we've been talking about rates of change, and rates of change are basically quotients. You're taking some unit dividing by some other unit. So, for example, you have total miles divided by hours, and you get a unit of miles per hour. I'm not sure if I've used the term yet. Hopefully, you saw it in the reading, but the term instantaneous rate of change, the rate of change at an instant, which is basically the slope of a curve at a point, in calculus is called the derivative, which is the really, really big idea that we talk about in calculus. So anyway, the last couple of days we've been really estimating derivatives. The second half of calculus talks about an idea known as an integral, and they're what are called indefinite integrals and definite integrals. We're going to introduce the idea of definite integrals here. So let's take a look at this. So a lot of the problems we've done up to this point were problems that involved some type of, maybe you had distance on one axis and time on the other. You'll notice in this graph here, we have velocity on one axis and we have time on another one. And so this is a car or some vehicle that's moving at a certain number of feet per second. Starts out maybe 45 feet per second, speeds up, and then it slows down. And the question here is, how far did this car travel over the course of 0 to 7 seconds? Well, from a pre-cal standpoint, we have absolutely no idea how to do that. And of course, the velocity is already the kind of thing that we were calculating before. So finding the slope of a velocity function would give us feet per second divided by seconds. That would be an acceleration, which isn't what this question's asking. So anyway, I want to step back to a problem that's a little bit simpler and look at the connection here. So let's say that this car had been going at a constant pace. Okay, let's say that it had been traveling at the same velocity. And I notice now, still have a velocity on this axis, but now it's miles per hour. On the other axis, we now have hours, okay? But let's say it was just traveling at a constant 60 miles per hour for 4 hours, okay? Well, most of you can probably tell me, if a car travels at 60 miles per hour consistently for 4 hours, most of you can probably tell me, oh, well, I would just take 4 times 60 and I would get 240 miles. That's how far this car went. Okay, but I want you to make a connection back to the graph. If you took 4 times 60, physically on the graph, what would you be calculating if you found 4 times 60? So if you look at that graph real carefully, what you would actually be finding when you take 4 times 60, you'd be finding the area under that velocity function. Okay, so there's my velocity function. 4 times 6 is 240. That's really the area under that curve down at the x-axis. That's what a definite integral is. It's the area under a curve down to the x-axis, under a function down to the x-axis. So we go back to that original problem. Same kind of thing here, okay? We've got a velocity function in feet per second, okay? And we've got seconds on this other axis here. You should be able to estimate the area under this curve. Now, all you can do right now, because we don't know real calculus and we also don't have the equation, all you can do right now is just count blocks, and you could get kind of an idea about how many blocks are under that curve. But technically, the area under that curve should tell you the total number of feet that this car traveled from t equals 0 to, I guess in this case, t equals 7. Okay, in another video, I'm going to come back and tell you just a little bit more about why that works, but that's kind of the founding idea of definite integrals. We'll add on more in a different video.